Covered mean as the measure of center for symmetric distributions. Now let's talk about standard deviation as a measure of spread or a measure of variability. Standard deviation is a number that we're going to calculate, and it measures how far away the typical observations are from the mean. Now, we know the mean is the typical value. That's what we would pick if we had to pick one number to describe what's going on. But we know not every person, not every object of study is going to be exactly that mean. Some will be a little bit higher, some will be a little bit lower. And so we need a number to describe, well, how high or how low were these numbers from the mean? How spread out is this data? And just like the mean, the standard deviation is appropriate if the distribution is approximately symmetric. It's not skewed left, not skewed right. We're going to use the mean for the center and the standard deviation for the spread or variability. Now, a higher standard deviation indicates the data are more spread out and the distribution is wider. A lower standard deviation indicates the data are closer together and the distribution is narrower. And this once again goes back to what we saw in chapter 2. We said the display had a low spread or a low variation if the data was all clustered together, very narrow. And if the data was more spread out in many different bars in a histogram, we said it had a higher spread. This standard deviation is going to be a numerical value that measures the spread between the values in a data set. So to put this into a context, let's look at example 1 here. It says these two histograms below show daily high temperatures in degrees Fahrenheit recorded over one recent year in Provo, Utah on the left and San Francisco, California on the right. Since these distributions are approximately symmetric, they're not skewed one way or the other really, the mean and standard deviation can be used to describe them. The means are similar. The average temperatures in these two cities are close. Provo has an average high of 67 degrees Fahrenheit. That's towards its middle of its distribution, somewhere in here. And San Francisco has an average high of 65. We want to know, well, how would their standard deviations compare? Which one would be higher and which one would be lower? For Provo, I can see this data is very spread out. I can see the lowest this goes is somewhere around 20 degrees Fahrenheit, and the highest this distribution goes is somewhere around 105, 108 or so degrees Fahrenheit. San Francisco, the lowest it goes is somewhere just above 45, maybe 47, 48. And the highest it goes is just above 90, maybe 92 or 93. And so I could say, well, this should have a higher standard deviation. And this should have a lower standard deviation. In San Francisco, the values are mainly clustered in the middle in these 4 bars, just a few on these outside bars. But with Provo, the temperatures are scattered all over the place. The data is more spread out. It has a higher spread, therefore it has a higher standard deviation. We want to do something similar in example 2. We have 3 histograms this time. They all have the same number of observations and they have the same mean, about 3.5. However, the standard deviations are different. We want to label the histogram that has the highest standard deviation and the histogram that has the lowest standard deviation. If I look at these 3, the one in green, the one in blue, the one in orange, the blue has the lowest standard deviation. It is more clustered toward the middle. It's not spreading its way out to the edges, but most are in these middle 4 bars. The one with the highest standard deviation out of these 3 would be the one in orange, the one on the far right. That's because it's the most spread out. Most of its observations aren't here in the middle around 2, 3, and 4, but most of the observations, most of the data pieces are on the far left-hand side at 1 or on the far right-hand side at 6. So we're spreading these data pieces out to the edges, and because it's more spread out, it has the higher standard deviation. Note that in this one, it's going up to about 250 observations in that particular area, and 6 about the same thing, whereas down here in green, we're not getting up that high. This is about 175 at the 1. 6 is also about 175, so not nearly as many on the outside edges. When your data is clustered toward the middle, the lower standard deviation. When it pushes out to the edges, then you begin to increase that standard deviation. I want to end this video with one more example about standard deviation before we calculate it in the next video. Standard deviation can be somewhat abstract as a number. So it's important to think about it in context. Well, what does it mean? What does this number tell us? The standard deviation tells us that a majority of the observations, or a majority of our data pieces, these typical values, are within 1 standard deviation of the mean. Most of your data, over half, should be within 1 standard deviation for the mean. For example, if the mean high temperature in San Francisco is 65 degrees and the standard deviation is 8 degrees, then a majority of your temperatures, most of your temperatures in the sample, are between 57 and 73. If you take your mean 65 and subtract 8, that gives you the low value, the 57 degrees. If you take those same 2 numbers and you add them together, that gives you the 73, your upper number. So most of the time, the high in San Francisco is between 57 and 73 degrees. Not every day, but most days. It could be a little bit lower, it could be a little bit higher, but that's where I expect most of them to be. Same idea in this final example. The distribution of high temperatures in St. Louis is symmetric, with typical values between 38 and 74. What is the approximate mean and standard deviation? To start with, let's look at the mean. The mean should be the center, what's in the middle of these 2 numbers. So I'm just going to add these 2 together and divide by 2. So if you take 38 and you add 74, that's going to give you 112. Then divide that by 2. We do that, that is going to give us 56 degrees. So this is my x bar. This is what my mean is. To get the standard deviation, we can use these 2 numbers. I took 56 and I subtracted some number to get 38. I took 56 and I added some number to get 74. Not 2 different numbers, but the exact same number. Well, that number, you could find several different ways, but it is 18. If you take 56 and subtract 18, that's going to give you the lower value of 36 degrees. If you take 56 and add 18, that would give you the upper value of 74 degrees. So our standard deviation, our S, would be 18 degrees.